Now let us go to the ML inequality, which helps us in estimating the absolute value or an upper bound on the absolute value of the integral. Okay, fine. So this is the statement of the ML inequality. For an upper bound on the absolute value of the line integral I, we have the following. Okay, so if this is the integral given to us along C, its absolute value, okay, is less than or equal to product of two things, okay, which are known as M and L respectively. L signifies that it is the length, okay, but what length? L is the length of the curve C, which is your path of integration, okay, and M is a real constant, obviously, such that for all values, for all points on the curve C, the absolute value of the function is always less than or equal to M, okay. And well, because it is a real constant, and because we are considering or talking about the absolute value of f of z, it is non-negative, and except for the zero function, it has to be positive. Okay, now the a typical problem on an ML inequality involves two parts, obviously. Part one is to find the length of the curve, which is perhaps the easier part, okay. And part two is finding the bound on f of z's modulus or absolute value, which is M. Okay, now this depends on what function you have. Okay, now some people think that ML inequality requires you to have let me put it in this way. The bound that you get on the absolute value of the integral need not be the least upper bound. Okay, well, the least upper bound would require you to actually find the integral itself. Okay, but even if you manage to find even a single real number M, okay, which exceeds all possible absolute values of the function f of z on C, that is enough. Okay, so if you come up with something else, okay, as your M, which exceeds the expected M or intended M, it is okay, because this is an inequality. So as far as the inequality is satisfied, we are happy. Okay, we are now going to see this through an example where it may be actually difficult to find the least upper bound. Okay, so even if we succeed in finding a higher bound, the ML inequality will obviously get satisfied. Okay, so let us now see a problem and try to understand the ML inequality better. Alright, the question says, use the ML inequality to bound the integral of e to the power z upon z squared with respect to z along a curve gamma, where gamma is a line joining the points I and 2. Okay, first things first, the function that we have here is e to the power z upon z squared, and you can see that it is defined everywhere on the, well, in fact it is defined everywhere except for the point 0. Okay, and the path of integration is not a closed curve, it is a straight line joining the points I and 2, and usually we will consider the sense of integration by considering the first point or first number here. So now it is from I to 2. Okay, so this is the straight line. You can get its equation right away. x by 2 plus y upon 1 equal to 1. Okay, this is the equation of the line gamma, if you want to call it, but this has nothing to do with the function itself. Okay, at least at this stage both are independent of each other. Only for the problem's sake they have come together. Okay, fine. So let us first find the easier part, that is the length of the curve. Use the distance formula to find the distance between the points 0, 1, which represents I, and 2, 0, which represents 2. Okay, the distance formula gives you the length as root 5, because this is 1, this is 2 and this is 1. Okay, let us now go to the process of finding m. Okay, so that all absolute values of the function f of z on that straight line in the first quadrant will be lesser than or equal to the number n. Okay, all right. Part 2 of the problem. F of z is e to the power z upon z squared. Take the absolute value. Okay, now in this problem, or in general in any problem on ML inequality, you should know properties of the absolute value. Okay, including the triangle inequality sometimes. Okay, fine. So if we take the absolute value of f of z, it is going to be absolute value of e to the power z upon z squared, which can now be written as absolute value of e to the power z divided by square of the absolute value of z. Again, all these things follow from the properties of the absolute value. Okay, now you may observe this, okay, or you may comment this. You may comment on this. If you want to find, or if you're looking for the maximum value of the mod f of z, the denominator should be minimum. Yes. Okay, now what is the denominator actually representing? The denominator is actually representing the square of the distance of that point on the z plane from the origin. Yes. Okay, so this is minimum at point P on the line where OP is perpendicular to gamma. Okay, one observation. And observation 2, when is the numerator maximum? When is the numerator maximum? Mod of e to the power z is mod of e to the power x plus iy. Split it, okay? And see, this is going to be purely real, and mod of e to the power iy is always going to be 1 because it is cos y plus I times sin y. So this is e to the power x's mod, okay, which is e to the power x. Okay, now when can you expect the numerator to be maximum? It is e to the power 2 at q, because at q the x value is the largest. Okay, so you now have already got I would say 1 m value. Okay, for that what you will do is you'll consider the maximum value of the numerator and the minimum value of the denominator. Okay, but we will find a better bound on the absolute value of the function f of z. Okay, all right. So in this part, in the next part of the solution, what we'll do is we'll try to find the exact point z at which the function mod of f of z achieves its maximum value. Okay, for this we will convert f of z into a function of only x or only y, because we know the equation of the path. Okay, and the important thing here to be noted is that absolute value of the absolute maximum value of the function f of z has to be somewhere between p and q. At q the numerator is the maximum and at p the denominator is the minimum. Okay, all right. So as stated earlier, the equation of line PQ is x by 2 plus y upon 1 equal to 1. Use this equation to eliminate y in the definition of mod of f of z. Okay, y is 1 minus x upon 2. Yes, and what is the absolute value of f of z? e to the power x upon mod of z the whole squared. Keep e to the power x as it is. Replace y squared in mod z squared by 1 minus x upon 2. There. Okay, so you'll get e to the power x upon x squared plus 1 minus x upon 2 squared. So this is now suddenly a problem on single variable calculus, finding the extreme value of the function. Okay, so if you expand it, the denominator's second term, and add it to x squared, the square term, you will get 5x squared by 4 minus x plus 1. Okay, now you can find the maximum value of this function provided x lies between 0 and 2 by applying the first derivative test. Okay, now I've already done that for you, and this is the graph of the function e to the power x upon x squared plus 1 minus x by 2 the whole square. Okay, and this graph is for the values of x which lie between 0 and 2. Alright, and you can see that this function has its local maximum at the point 0.8. Okay, x is equal to 0.8 and the value is 2.226. Okay, but what I have done is I have actually found out the exact expression for, or exact value of m. Okay, it is an irrational number for sure. Okay, so how to do it? Just substitute x as 0.8, and because x and y are the coordinates of a point on that line, get y by applying the formula 1 minus x upon 2, or 1 minus 0.8 upon 2, 1 minus 0.4 or 0.6. Okay, fine. So now use the ML inequality. By ML inequality, the absolute value of the integral f along the curve gamma has to be less than or equal to ml, and have we found out m now? Yes, we have. Okay, e to the power 0.8 or e to the power x divided by x squared plus y squared, or 0.8 squared plus 0.6 squared, this should be 1, into this is L, which we found out in the part 1 of the problem. Right? Yes. Now if you simplify it, it will turn out to be e to the power 4 by 5 into root of 5. Okay, now the main time consuming process or part in the solution is finding the extreme values of the, or extreme value of this function. Okay, so if the problem doesn't demand you to find the least upper bound, so to speak, what you can do is you can find a bound which is worse than the best bound that you can find, but at the same time this will be easier to find. The first one was more difficult to find, but it was a better bound. This is a worse bound, but this is easier to find. Okay, and even we have talked about this at the beginning of the solution. Okay, for finding a bound on an upper bound on the absolute value of f of z, go to the maximum value of the numerator and go for the minimum value or the least value of the denominator. Okay, the maximum value is e to the power 2. Yes, and what is the minimum value of the denominator, or x squared plus y squared? For this, use the formula for length of perpendicular from a point on a line. What is the point that we have got? Origin? Yes. And what is the line that we have? Gamma. Okay, and its equation is x by 2 plus y by 1 equal to 1, or minus 1 equal to 0. Okay, see, now this is actually square of the length of perpendicular. Okay, so don't forget to square it, and it is ax1 plus by1 plus c upon root of a squared plus b squared. Substitute the appropriate values, a as 1 upon 2 and b as 1, and of course c as minus 1, and x1 y1 to be zeros. Okay, so if you do that, it will turn out to be 4 upon 5. So this is the denominator. Okay, so now what we can take m as, now what we can do is we can take m as e to the power 2 divided by 4 by 5, or 5 times e squared divided by 4. L will not change, so the integral has to be less than 5 e squared upon 4 into root of 5. Okay, now let's just compare the two bounds. Okay, this was worse but easier, better but difficult to find. So there we had got m as e to the power 4 by 5. Okay, and if you multiply it by root of 5, okay, the approximate value will be 4.98. So I has to be less than or equal to 4.98. Okay, and the next m value that we have got, the easier way to find it is 5 e to the power 2 upon 4, and if you multiply it by root of 5, that is L is not changing in both the cases obviously, it will be 20.65. Okay, see, now this is almost 3 times 4.98, okay, or even 4 times. Okay, however, if you have got a value of the integral, let us say 22 or something like that, then you can be 100% sure that, or absolute value of the integral, then you can be 100% sure that there is something wrong. Okay, fine. So this is how you apply the ML inequality to find an upper bound on the absolute value of the definite integral, or absolute value of the line integral defined on a complex, or of a function defined on the complex plane z, that is z plane.